An entirely different approach to making your code less buggy is, instead of using a bug-prone language and finding the bugs, switch to just using a better language. There are some well-known desirable language capabilities. These include type safety and strong typing. In other words, having pointers and ints be the same data type is pretty much a bad idea, even though that's what C does. Maybe you want memory safety, where the bounds and arrays are actually checked automatically instead of you having to do it. Maybe you want some robust static analysis built right into the language rather than having to buy expensive fancy third-party tools. In general, a desirable language capability is there are no surprises. Well, it turns out such a language already exists and has been around for decades. It's called Ada, named after Lady Ada Lovelace, who was the first programmer. And here's an example program interface in Ada. This is the interface to a subroutine that increments a value. The value to increments is x, and it's a counter type, both input and output. The with clause tells you what the interface does. For example, there are no global variables, and the output x only depends on the input x. There's a precondition that x must be less than the maximum counter type, and there's a postcondition that the new x will be the old x plus 1. Note that this is not actually the code. This is the interface, which allows you to check things like proving that programs will never overflow a counter because you know what a counter does and you know what the interface looks like. The actual code to increment the value is actually pretty straightforward. You add 1. Ada's gotten a bad reputation because it was a very complicated Baroque language, but a subset called Sparkada is getting traction as a safety-critical language. So it's a subset of the full Ada programming language that just keeps the good parts. It's a formally defined language, so you can verify programs mathematically. The language does not have ambiguities and does not have undefined behaviors, which obviates the need for a lot of the things that you saw in the MISRA C rules. You can actually prove that a program is correct. For example, you can prove before you ever run it that you will never overflow an array index, you will never divide by 0, and so on. Now in practice, when you write code, what you find out is you fail the proofs, but that's okay. This is static analysis on steroids that really gets you to get your code cleaned up before you can actually get past the compiler. A key idea is design by contract, where those preconditions and postconditions and side effects we were talking about are defined in advance, making it harder to have defects caused by mismatched expectations between different parts of the code.